Hello science fans! Today we're exploring the fiery world of cement making, where heat transforms simple rock into the backbone of our cities. Making cement is like baking a special cake. You need limestone, clay, and, most importantly, intense, controlled heat. Without the right temperature, you don't get strong cement, just a pile of dust. It's the heat that creates clinker, the essential ingredient in cement. Like toasting bread, too little heat leaves it weak. Too much ruins it. Cement needs a precise temperature window for the right chemical reaction. If the temperature is off, the cement is weak or unsafe. Bad news for buildings and bridges. Cement plants burn huge amounts of energy to reach these temperatures, so efficiency matters for both cost and the environment. By carefully managing heat, engineers make the process more sustainable and reliable. But how do they control such extreme heat? With advanced thermal sensors, rugged high-tech thermometers built for the job, these sensors constantly feed data to operators, allowing precise adjustments. It's a delicate dance of fire and rock, all orchestrated by the power of measurement. Let's see how this works inside the heart of the process, the kiln. Meet the rotary kiln, a massive, slowly spinning steel tube, longer than a football field. Raw materials enter one end, tumbling down as the kiln rotates. At the lower end, a roaring flame blasts air hotter than volcanic magma, over 4,450 degrees. As materials move through the kiln, they pass through temperature zones. Water steams off, limestone releases CO2, and finally everything fuses into marble-sized clinker. Measuring temperature inside this inferno is a huge challenge. No ordinary thermometer survives here. Sensors must withstand extreme heat, abrasive material, and corrosive gases. Controlling the kiln's temperature profile is critical. Too cool, and the clinker is weak. Too hot, and you damage the kiln and waste fuel. Engineers need to know the temperature of the material, gas, and kiln wall. Specialized tools are designed to survive and deliver this vital information. Let's look at the technology that makes this possible. Enter the thermocouple. How do you measure heat that would melt steel? Enter the thermocouple, a simple, ingenious device. It's made of two different metal wires joined at one end. When heated, they generate a tiny voltage, thanks to the Seebeck effect. The hotter the junction, the higher the voltage, allowing precise temperature calculation. Different metal pairs make different thermocouples. Media group, assortment of thermocouple wires labeled with type letters. Comparison chart of thermocouple type is a Stocker distribute equally. Type K for up to 1,250 studies. Type S for the hottest spots near the flame. These wires can't just dangle in the kiln. They're protected by tough ceramic or metal sheaths called thermowells. The thermowell shields the sensor from heat, abrasion, and corrosive gases. Thermocouples are the kiln's nerve endings, delivering real-time data from the heart of the process. But for cooler, more precise measurements, there's another tool. Let's meet the RTD. For precision, in cooler zones, engineers use RTDs, resistance temperature detectors. RTDs use platinum wire. As temperature rises, so does its electrical resistance in a predictable way. This makes RTDs extremely accurate and stable, perfect for monitoring bearings, gearboxes, and cooling systems. However, RTDs can't handle the kiln's extreme heat. They're limited to about 600 degrees Celsius. They're more fragile and costly than thermocouples, but their accuracy is unmatched in the right environment. You'll find RTDs in grinding mills, silos, and on motors. Anywhere a few degrees matter. Choosing the right sensor is all about matching accuracy, durability, and temperature range. But what if you need to measure heat without touching it? That's where infrared pyrometers come in. Let's see how they work. Sometimes you need to measure temperature from a distance. Enter the infrared pyrometer. Everything above absolute zero emits invisible infrared energy. Hotter objects emit more. Pyrometers act like special cameras, detecting this energy and converting it into a temperature reading. In cement plants, pyrometers are essential for monitoring the burning zone and scanning the kiln shell for hot spots. Operators aim pyrometers through kiln openings to get instant, accurate readings. Crucial for process control. Pyrometers also help spot problems like worn-out refractory bricks before they become disasters, but there's a catch. Readings depend on a property called emissivity, which can change with dust and surface conditions. Getting accurate results means adjusting for emissivity and dealing with interference. Engineers have a clever solution for this challenge. Enter the ratio pyrometer. Let's see how it keeps a clear view in the harshest conditions. 12. Inside a cement kiln, dust and smoke can block a standard pyrometer's view, leading to false readings. Ratio pyrometers solve this by measuring infrared energy at two wavelengths and calculating their ratio. Dust affects both wavelengths similarly, so the ratio cancels out the interference. This allows ratio pyrometers to deliver reliable readings, even in the dirtiest, hottest environments. Operators can trust these measurements to fine-tune fuel and airflow, improving efficiency and product quality. Ratio pyrometers are a game changer for continuous, accurate monitoring. They help extend kiln life and ensure consistent clinker quality. It's a perfect example of smart engineering overcoming tough challenges. But even the best sensors need regular checks. Let's talk calibration. Sensors can drift over time. Heat, vibration, and dirt all take their toll. Even a small error can cause big problems in cement production. That's why regular calibration is essential. comparing sensor readings to a trusted standard. This process, called traceability, ensures accuracy from the plant floor to international standards. Critical sensors are checked often, less vital ones, less frequently. A strict calibration schedule keeps the plant safe, efficient, and profitable. Proactive calibration prevents problems before they start. It's like a regular checkup for the plant's nervous system. Now, how do you calibrate sensors that face such extreme conditions? For thermocouples and RTDs, engineers use dry block calibrators, portable furnaces with precise temperature control. A reference probe and the sensor under test are placed side by side. Readings are compared and adjusted as needed. This is repeated at several temperatures to ensure accuracy across the range. For pyrometers, calibration uses a blackbody furnace, a perfect source of infrared radiation. The pyrometer is aimed at the blackbody, and its reading is checked against the known temperature. Ratio pyrometers are calibrated similarly, ensuring reliable performance. Accurate calibration is vital for process control and product quality. It's a high-tech tune-up for the plant's most important sensors. Reliable temperature data is the backbone of cement plant operations. Maintenance is ongoing. Keep sensor lenses clean, inspect thermowells for damage, and check wiring for faults. RTDs need protection from vibration. Pyrometers need clear lenses. Regular calibration and detailed records help spot trends and predict failures before they happen. Proactive replacement of aging sensors prevents costly downtime. Every sensor, from rugged thermocouples to precise RTDs and clever pyrometers, plays a vital role. They form the plant's nervous system, enabling safe, efficient and sustainable cement production. Mastering heat means mastering measurement and maintenance. That's how engineers ensure every bag of cement is strong and reliable. And that's the science behind the world's most essential building material.